Guys, so today we are going to start by talking about electricity, and the whole unit's going to be on electricity and magnets. And I know they don't seem like they're very related, but they're extremely related, and we're going to get into why in just a few days. So electricity, where does it come from and what exactly is it? So electric charges are from protons, and protons are positive because they have that letter T in the middle, and that T means they're positive, and electrons are negative. It has the E in the very center of the electron. If you look right here, it's got that little negative sign across the very bar of the word electron, so that means they're negative. So those electrons are positive those charges are from protons and electrons, which are positive and negative. So the accumulation of excess electric charges on something is static electricity. So that's like when you get shocked. If you're at Walmart and you touch the basket and you get shocked, that's static electricity. If you rub your feet on the floor really hard and touch your friend and you shock them, that's static electricity. Or if you've ever rubbed a balloon against your hair and pulled it out and watched all of your hair stand on end, that's because of static electricity. Atoms become charged by gaining or losing electrons. So all of this has to do with the subatomic particles that are inside those atoms that make up both you and me and everything on Earth. Let's explain this a little bit better. So we have static buildup on our shoes. So sometimes atoms are bound super, 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 super tight, and the electrons are really, really, really attached to what they're in. So the electrons in your shoes and the rubber are really, really, really tight, and those electrons are bound super, super tight, and they're not going to go anywhere. But the electrons in the carpet aren't bound so tightly. They're able to move. So those electrons rub from the carpet and they transfer from the carpet to the positively charged protons in your shoes. So when they transfer to those positively charged protons in your shoes, now there's more positive in the carpet and more negative in your shoes. So you have extra negative charges. And that's what makes things stand up on end. That's what allows you to shock people, is that transfer of those negative charges and a buildup of negative charges on one side and positive charges on the other. So the law of conservation of charge says that electric charges can be transferred from one object to another, like in the shoe example. We can transfer those negative electrons from one object to another. But we can't create or destroy energy. We've said that before. We said the law of conservation of energy meant we can't create or destroy energy. So the law of conservation of charge is saying we can't create or destroy those atoms and those electrons either. They have to go somewhere. They can't just disappear. And those positive and negative charges exert force on one another. So positive and negative, you've all heard the saying before that opposites attract. The same is true in science. So your positive proton is attracted to your negative electron. And like charges push each other apart. So if you have two positives, they push away from each other. And if you have two negatives, they push away from each other. Just like in people, if you're too alike somebody else, you usually don't get along. Your personalities clash because you're so much alike. So the same thing happens in science. If you're both positive, you don't get along. You get pushed apart from one another. The same thing if you're both negative. You push apart from one another. You don't want to be close to that person. And those charges exert forces. So the force between those electric charges depends on the amount of charge as well as the distance between them. So as the amount of charge increases, the force increases. So the more and more and more and more buildup of electrons on something, the more and more negative it is, the more and more force it's going to have. The same thing happens as the charges get closer. So the further away they are, it doesn't really have that much of a pull on it. If a balloon is on the other side of the room, it's not going to let your hair stand on end. But if the balloon is really close to your hair, it's going to stand on end. That's because that charge, that negative charge in the balloon, is attracted to your hair when it's super close, but as it gets further and further away, it loses that pull. So this little picture of a kid is a great example of static electricity. And he's supposed to be static electricity in a dryer. So when you put your clothes in a dryer, all of your clothes are tumbling on top of each other and rubbing on top of each other. They're directly touching, so those electrons are directly transferring from one atom to another in something else. So some of your clothes especially the bigger items, if there's a lot of smaller items in there, those electrons are going to transfer to those big items, and those big items are going to have a buildup of electrons. Well, if these guys have a buildup of electrons and these guys have a buildup of protons, they're going to be attracted to one another. And that's why when you pull things out of the dryer, a lot of times you have socks and different things that are stuck to your clothing, or they're all stuck together and you have to pull them apart. When you pull them apart, what you're seeing when you see the sparks and hear that, you're actually seeing and hearing that transfer of energy. But charges don't have to be touching. Like I just said, that balloon can be across the room. It doesn't have to be touching my head. It could be like right here, and my hair might still stand on end. So an electric field surrounds every electric charge and exerts the force that causes them to be positive and negative, attracted and repelled. So the arrows show us how the positive charges would move. So a positive charge is going to move away from another positive charge because they're alike and they don't get along. And a positive charge is going to be attracted to a negative charge because opposites attract. Conductors versus insulators. So a conductor is a material that can charge by contact. It's something we can run. A conductor is a material in which electrons move easily. It's something we can run electricity through easily. Think metals, especially copper. They're some of our best conductors. We can run electricity through them. When you want to think about something that's a conductor, think about substances that when you touch them, they can get hot. Insulators are materials in which electrons really don't move that easily. A lot of our woods, our plastics, our rubbers, those things are going to burn and light on fire before they heat up. So those are all going to be our insulators. We can charge things different ways. We can charge things by contact, meaning they have to touch. So that's just by touching or rubbing two things together like this, we're transferring those electrons and we're charging something. Another way we can charge something is by induction, and that's when we actually rearrange electrons on an object that's neutral. We're going to get a little bit more into that in the days to come. We're going to get deeper into all of this in the days to come. This is just the tip of the iceberg. The last thing I want to talk about today is weather and lightning. So a lot of y'all know lightning. You've seen lightning, especially living in the South. Both of them are both getting shocked, and lightning are the same thing. I said earlier, like when you pull the clothes apart in the dryer, you see those sparks. That's lightning on a tiny scale. So they're both static discharge. So the static discharge is the transfer of charge between two objects because of the buildup of static electricity. So what happens is this thundercloud is big, big, big in the sky, and it generates static electricity because air masses are moving and swirling, and they're creating areas of positive and negative electrons as they shed on one another and as those electrons and protons get transferred. So eventually static discharge is going to form. And as the electrons move through the air and as those charges move through the air, they collide with atoms and molecules. And those collisions cause the atoms and molecules in the air to emit light. Thunder is electrical energy. So electrical energy rips electrons off atoms in the atmosphere. The electron is needed somewhere else, and so it's literally ripped off and pulled to a different atom. And that produces heat. And the heat causes the air to expand super rapidly. So when the air expands super rapidly, more air has to come in to fill that void. So what you're hearing is the sound of the air filling in that void. So the lightning happens first, and then the air fills that void, and you hear the thunder. It's a little bit easier to see in a picture. So you've got ground to cloud lightning. So you've got your negative and your positive charges here. You can have cloud to cloud lightning, cloud to air lightning, or cloud to ground lightning. And grounding is a path for those charges to reach the earth. So on Earth, I just said that you could also be negatively and positively charged. Lightning is going to travel the path of least resistance. It's going to rip electrons from the easiest place it can rip them from first. So it's going to pick things that are closer to the sky. It's going to pick things that are more charged than others and things that are better conductors than others. So it's not going to pick, if anyone's ever told you, when I was little, I was scared of thunder and lightning, like most kids are. And my grandmother used to always tell me to put on rubber shoes because lightning couldn't get me in rubber shoes. While that's not 100% true, the rubber shoe thing was. Rubber is an insulator. It can't conduct electricity. So I wasn't shedding enough electrons in those rubber shoes to allow static discharge to build up on me. So the lightning literally wouldn't be attracted to my shoes because I didn't have static discharge on them. So grounding is what provides a path for the charge to reach the earth. And a lot of times we use an object that we call a grounding rod or a lightning rod. And that is how we're going to redirect that electricity, that static discharge from the air into the ground. So it doesn't hurt anybody or hurt anything, because lightning can be extremely dangerous. And it doesn't always have to happen when there's bad weather around. Lightning can happen when there's good weather around. The craziest lightning I think I've ever experienced was, they call it snow thunder and snow lightning. So you can't hear anything in the sky, there's no rain outside, and all of a sudden you see these big flashes. You've also probably, living in the South, seen heat lightning, which is the same thing. It's just the transfer of electricity. These pictures at the bottom are of sand sculptures. So what they do is they put a lightning rod in the sand. So there's more static discharge. There's more electricity attracted to that lightning rod than there is to the sand beneath it. So the lightning hits the lightning rod and it heats it up. And then that metal conducts the electricity safely and soundly into the earth. It also heats things up. It conducts it and transfers it by heat. Well, when you heat up sand, it makes glass. So a lot of people like the way it looks. So they put the lightning rod in the ground, and then you can see how the heat and the energy was dissipated and moved around through the ground by looking at all of the different sand that's formed into glass. Obviously, these are still in their raw state. They take them, they clean them up, they get the sand off the outside, they shine them. If you want to see some great examples, the movie Sweet Home Alabama has lightning rods and a whole store of lightning rods at the very end of it. So here's a little bit better picture. So here's your lightning rod. It intercepts the electric discharge and conducts it safely to Earth. So they're installed according to their reference standard. It's different for every lightning rod. And it's got a down conductor, an earthing system, a surge protector, so that lightning isn't transferred, the energy from the lightning isn't transferred to the electricity in your houses. A lot of times also in houses now, we have ground wires and grounding, and that's going to help if our house does get struck with lightning. The last thing you need to know about is an electroscope, and that's just a device that can detect an electric charge. So this is a very rudimentary electroscope that I have a picture of, but you've got aluminum foil leaves, and whenever you have something that's positively charged, it's going to attract the positive protons, and those negative leaves are going to push apart from each other, and it's going to let us know exactly how much electricity there is in, or how much charge there is in whatever object is on top of it. And that's all for today.